Hello friends, welcome to the 7th experiment of our DSP lab. In this experiment, we are going to see the application of Hilbert transform. In the last lecture, we have already seen what Hilbert transform is. So to brief it up, it is a linear operator with the function 1 by pi t. When applied with the signal, it gives a phase shifted version of the given signal. And it is represented as minus j signum of omega. For more information, see my previous video. So here we are going to see where do we use it and what are the applications. So basically, if you see in a power line, you are giving 50 Hz sinusoidal signal, but then when the load is more, the amplitude of the sinusoid decreases, and at the same time when the load is less in the power line, the amplitude hikes up. So like these things causes glitches and it may harm our devices. So over there we try to find the change in the amplitude, and sometimes when a signal has multiple frequencies, how do we detect the what all frequencies present in the signal? So for all this purpose, we are going to use Hilbert transform, and we'll be seeing how it works. So the first one is that when a signal consists of multiple frequencies, how are we actually going to detect? And using Hilbert transform. So here I am using a signal consists of two different frequencies, namely 30 and 60, half the time period of the total given length. I am sampling at 600 Hertz. Then it's like as usual process, make it into frequency domain. From the frequency domain, find the Hilbert transform and convert it into time domain, and then get the magnitude and get the phase out of it. We are going to do the same procedure here. Capital Y represents the frequency domain representation of the small y signal, time domain signal, and then like here I am initializing the IDFT of y. So x is the frequency response. So here we are finding y of k. Y of k is a kth coefficient of the frequency domain signal computed for n time domain signal of y. So it's a normal equation, e power minus 2 pi by n k into t. Here k minus 1 I am using because MATLAB starts from 1. Index starts from 1. I am also starting at 1 to fs, but it should be 0 to fs minus 1. So I am calculating over here, and then I will be plotting what are the components present in y. So from there also we can find the frequencies component, but still here we would like to use Hilbert transform. So we are trying to find the time domain representation of Hilbert transform after applying Hilbert transform. So whenever the k is positive, it is multiplied by minus j. Whenever the k is negative, it is multiplied by plus j. And then we are finding the IDFT of y, which is the normal expression e power 2 pi by n k into t. Here the same expression goes for k minus 1, and here into y. The reason why I am using conjugate of y is when I am transposing of y, which is a complex number, inbuilt MATLAB function gives a conjugate of y as well. So we don't need a conjugate. That's why conjugate of a conjugate is again the normal signal. That's why I'm again using conjugate. And then we have a scaling factor of 1 by fs. So with this we found the Hilbert transform of the given signal. Now we make the total analytical function with the given signal y and the Hilbert transform. So now we got the signal. Then this signal has all the magnitudes, phase and amplitude response that we are interested in. So we are trying to find what is the amplitude of what is the phase of the signal. So we'll be having tan inverse of y by x, and a tan 2 needs to be unwrapped to be detected by the variable. So then now frequency component we got, it is something in the form of 2 pi fs into t plus some constant, but here we need to find the frequency response, so we are differentiating it, and there is some scaling factor happening over here, and then we are plotting what is a differentiated value. So let's see, is it giving the required component or not. So we are running it, and then so here we can see this is our input signal, has two different frequencies. This is 30 hertz and this is 60 hertz. We are computing in frequency domain, so we can actually see 30 hertz and 60 hertz component present. And after computing the Hilbert transform, like we are plotting the phase shifted version of the input signal. So this is again 30 hertz and 60 hertz, and then we are finding what is the phase between this signal and this signal to read the frequency component. So after differentiating it, we are getting two lines. What are these lines and what do they actually represent? If you see the value over here, it is 30, and the other value over here is 60. So these are the ripples due to other phenomena like differentiation properties. So we are not interested, but we are interested in average value, at what mean value they are making, they are standing by. Here we are seeing it's 30 and 60. These two represents the frequency of the signal, as we have used 30 hertz signal over here and 60 hertz signal over here. So with this, now we come to know how to use Hilbert transform to find the different frequencies present in the signal without using the peak detection in frequency domain. So then we'll now move to decay rate. So we'll comment it out. So then now the amplitudes are degrading. So how do we find the what rate it is degrading at? So for that also we are using Hilbert transform. Here also goes the same way. The input signal we are taking is e power minus alpha n into some sine components. So it's a normal sine wave having a decay rate of 4. So we need to get this particular 4 value from the equation. So how do we do it? It's again the same value, same method. We'll be finding the frequency domain representation and finding the Hilbert transform and multiplying the frequency domains, and then we'll be calculating IDFT of the frequency domain. Then we'll be plotting analytical signal. So now in the analytical signal, where does the information lie? Information lies in the amplitude. So we'll be finding the amplitude of the signal. So now the amplitude response will be something like e power minus alpha n. We need to find the alpha out. So we are finding e power minus at can be, where alpha can be taken when ln is applied. So here ln is applied, ln is equal to log of something by log 10, that becomes ln of the amplitude. So now once you apply the ln, you will get minus alpha into n. So you have to divide that n as well. So I am dividing by n. Here I have defined n as t. The reason why I am choosing 2 is because I have defined t starting from 0. When I do division by 0, it gives undefined value, math error. So I am starting from index 2, where it starts right next to 0. So let's see how it works. So we are getting the plot. This is our input signal, and these are the frequencies present. That is because of this sinusoidal signal. And we are finding the Hilbert transform of the signal. Then we are finding the what is the amplitude of this signal, which we can actually see here. It is something like e power minus at, and with this we are going to find the decay rate. As I have already ran the program, this decay rate is printed over here. It is 4.09, and the decay rate we gave is 4. So basically we are able to derive the equation, derive the decay rate of the signal. So from the decay rate, we'll be able to know whether the signal is having a heavy load or no load or less load than the requirement in the power line signal. So then again I will be commenting out. We'll move forward to do the peak detection using Hilbert transform. The normal way of peak detection is by differentiation, like that's what we have seen in the previous videos. But peak detection by differentiation may not give the correct result in all the time, and you have to give a threshold value and all those stuff. So here we'll be using just the Hilbert transform to see the peak detection. So here we'll be using the new function is which is 1 by 1 plus t square. It is a bell-shaped curve, and its Hilbert transform is its Hilbert transform crosses 0 whenever the bell-shaped curve goes to its maximum. It means whenever the maximum occurs, the Hilbert transform have a 0 crossing, which is similar to what we have in differentiation. So let's see how it looks. So here basically what I am going to do is just I will be showing you what is the how does a signal look like in time domain, and what is the Hilbert transform of the signal in time domain. It's again the normal process where I will be finding the frequency domain response, multiply with the Hilbert transform, and get the Hilbert transform back. So let me plot it. It's plotting. Let me close it here. Okay, let me again run it. So it's again here. We can actually see the input signal 1 by 1 plus t square, as it is symmetric along the axis. Here I have considered 0 to 200 with the mean of 100. So it is 1 by 1 plus t minus 100 whole square. So here you can see the bell-shaped curve, and this is the Hilbert transform of the signal. You can see it goes to maximum at 100. At the same time, Hilbert transform crosses 0 at 100. So with this thing, if there is any signal which is having a peak at some value, Hilbert transform will be giving a 0 crossing over there and having an abrupt change in its magnitude. So we will see the practical example of how do we use it. So I have made an example where signal is having a multiple amplitudes, multiple peaks. So let's see like whether the function works correctly or not. Though it has certain drawbacks, it works in most of the cases, and it's easier to compute. So I'll be uncommenting it. I'll show you. Here again I am taking a signal from minus 10 to 10 and I am plotting it. But now I am generating a new signal that has multiple amplitudes. So I am making 5 sets of this from minus 50 to plus 50. From one length I am making 0.6 of its version's amplitude, and the other length I am making as 0.8, and the other one I am making as 1. So it goes in. I have 5 different values of this signal concatenated to make a new signal. So let's see whether the this Hilbert transform works to find the peak of this signal or not. So here again the same procedure. We'll be finding the inverse. We'll be finding the frequency domain, Hilbert transform, then here inverse. Then we'll be plotting the real part of the signal to see whether at every 0 crossing of the Hilbert transform do we have the peak or not. So let's see. Let's run the function. So this is our function. Here you can see I have 5 different sets of value with different varying amplitude, and you can see Hilbert transform is having a 0 crossing over here with abrupt change in its magnitude. So with this we are able to find the peak of the signal using Hilbert transform without using any differentiation. So these are the applications. These are certain applications of the Hilbert transform, and from this we can't conclude that it's completely reliable, but in most of the cases it is. There are some exceptional cases where it is not reliable. We'll look into that in the future videos, and I hope you enjoyed this video, and thanks. That's it.